Okay, so last class. Okay, first few announcements. This is not for this course, but for the department as a whole. There's an undergrad town hall that is going to happen today from 6 to 8 p.m. Please try to be there. I'll be there at least for part of it, and other faculty from the department will also be there, including the chair and the undergrad vice chair. Okay. And homework 4 is already up on the website. It covers until this lecture. So, the last 2 problems are based on material from this lecture. So just hold on until you understand this lecture. And of course, next Wednesday, November 16th, we have our second exam in this room and again, the adjacent room. And the exam covers lectures 9, 10, 11, 12, 13, 14. So 6 lectures, roughly each lecture will contribute maybe about 4 to 6 points. Okay, again, it's kind of average. It's not a hard line because, some proofs spill over and so on, but that's about the rough distribution. And the format is similar to exam 1. There'll be a few objective questions and then a few problems. As I keep saying, definitions more important than the theorem statements, more important than the proofs. And try to know how to use the proofs when needed to. In terms of practice, look at the homeworks, their solutions, practice problems within the homework. There's some additional problems within each homework. I asked the TAs to even add solutions for the practice problems, and they should be able to do it soon. You can also look at the last 2 years' exams. And just as a warning, though, we are ahead by a lecture because I cut out some material compared to last lecture. So for instance, don't just look at exam 2 from fall 21, also look at exam 3. Some problems relevant for lecture 14 in particular are in exam 3. Okay. So let me just say that here. All right. And the TAs this Friday will do more practice problems on pumping lemma and reductions, which we are going to cover today. And if you're looking for even more problems, then Sipser's textbook has plenty of them. You can access them. Some of them could be challenging, so kind of, just take it as they come. Okay. Any questions about the exam? Yeah. Oh. Okay, so I didn't think of that. The TS will do more practice problems. That's what I had in mind. Yeah. Okay. We'll, post more. Okay, but in any case, if you come across any problems, these are all the questions that we have. If you come across other resources, some question or some topic is not clear, even if it's Veterans Day holiday, I'll be there to answer questions, through Saturday and Sunday. So, just go ahead. Okay. All right. And yeah, try all these other sources. We'll also include some additional questions for your practice. Any other questions? All right. So if there are no other questions, let's go ahead to the actual lecture. So last class, we talked about having our cake and eating it to principle. So when designing things in terms of Turing machines, for the most part, we can speak in terms of higher level programming languages. You can write code in Python and assume that everything can be translated into a Turing machine because there is a theorem which says you can do it. All right. And we also saw some evidence for it. Like we saw some examples of doing it, and it is also possible to do in more generality. We also saw the important notion of universality, that the eval function, which is a completely well-described function, is actually computable by a Turing machine, right? And that is something, again, will show up today as well. And finally, we took a step towards understanding the limits of computation. Can computation, can you compute any function that you want? So that's a very fundamental question, is every function computable? And we kind of said that that is not true. As unfortunate as that is, you cannot compute every function, no matter how much time you give yourself. There are some functions like the toddler function, which we define, and we'll show that this function, toddler, is not computable. Okay. And we'll use that as kind of our lever to show that many other interesting problems become uncomputable. Okay. Toddler is kind of a curious function. It seems interesting, but completely impractical unless you have a toddler. But there are other important questions that are relevant in practice that also turn out to be computable, as we'll see examples of today and in next week. Okay. So before going ahead and talking about why the toddler functions are computable, I also asked you to kind of spend some time trying to digest the definition of the function, because it's a few lines, but I think it's very confusing unless you understand what's really happening. So it's confusing mainly because it has this meta nature to it. So let's understand what is that. Okay, so what do you mean by understanding code as data, right? So often when we think of like, let's say I have an algorithm, it's maybe running on this laptop here. It can take any input. It takes some input, some binary string, text file or whatever as input, and then produces an output. Okay. And so the main thing that we are trying to understand or exploit is that for any program, there's nothing that prescribes what this input should be. Okay. You often imagine, okay, this is a program which only handles images, so only images should be given as input. But it's not really true. If you give something else as input, it still has an output. It says invalid input, which is a valid output again, right? So there is always an output defined, no matter what binary string you give as input. Okay. So this can be any string. Okay. And what we are trying to say is we can give the description of another program. Okay, also as input. Okay, so you should think of description as really just like source code, right? If you have a function, you have a function handle. If you're in programming language, if you're in Python, you can refer to a function handle, like that's a function handle. Description is just the source code of the program, okay, of the function. That's it. That's the correspondence between M, like we say this is a Turing machine, okay, or you can think of it as a program, right? And then when we say it's description, which we said we'll denote with this angle brackets, which is a binary string, is really just like the source code of the program viewed as a string. Okay, you're just viewing the source code as a string. You're not kind of giving any semantic meaning to it yet. You're just viewing it as a string. Okay, just a dummy example. We can see it here. Why is it so? Okay. Okay. So here I've written a simple function, invert string, which takes a string as input and just writes down all of the characters from the string in reverse. Okay, I can ask it to run that. And then there's a file, read text from file, which takes a file name as input and reads whatever is in that file as a single string and returns the string. Okay, so if I ask it to run invert string allow computer science, then I get whatever. If you read in reverse, this is what you get. Okay, very simple. And Turing actually also did many other things. He wrote a paper called Imitation Game, which tells about how you can check whether an AI has developed true intelligence or not. So I loaded that into this text file. I propose to consider the question, can machines think? Imagine starting a paper with that title, with that first sentence. Okay, I can read that whole text into a file and run the invert string, kind of prints all of this stuff. Very messy, but if you go to the end, you start reading in reverse, it's like, the imitation game, next line, something, something, I propose, whatnot. Okay. All right. So invert string can take any string as input, right? Now in Python, it's actually possible to extract the source code of a function pretty easily as a string. Give me any function, and this is something called inspect. I can use it to get the source code of the function. If I call it on inspect.getSource invert string, it's going to return me a string. You can check the type, this string. If I ask to print that string, what is it printing? Exactly the source code. Okay, so this is what a description, this is what our angle brackets is supposed to be. You have a function, the description, the source code is what our angle brackets are. For Turing machines, the source code, of course, is not as neat. It's not formatted this way. It's not indented or anything like that. Something messier. There's a messier encoding with binaries with only zeros and ones. But the principle is the same. And I can call invert string on its own description. There's nothing that prevents me from doing that. Okay. And this is what you get. Okay. So I can run a function on any string. And here, what I'm asking to do is run the program on its own description, which is a valid thing to do. Okay, we just did it. All right, let's go back. Okay. But so just keep this in mind, right? This correspondence, I think, is helpful. Okay. Now let's get back to what the toddler function is doing. Right, so recall the definition from last class. Okay, so toddler takes a string as input, which it views as a description of a machine. Okay, it knows it's the source code of some program. Right? And then runs the program with that source code on its own source code. Okay? Exactly what we did. It doesn't run it, but if you run it, whatever the output is, based on that, it is defined to do something. Okay? If starts with a 0, output 1, and is 0 otherwise. Okay, so two things can happen here, right? I have this source code. I can give it as input to the machine M itself. And when I run it, two things can happen. Maybe I got a valid output, or I got stuck in an infinite loop. Right? So Turing machine can, if the machine terminates, then the output is defined as whatever was on the tape until the head. But if it did not terminate, then there was no output, which we denoted by saying this is right? So what toddler is saying is, for instance, if M on M does not terminate, what is toddler defined to be? If it does not terminate, what should the output, what is this quantity toddler of M? If M does not terminate, then it should just be 0. Okay, because we defined it as a negation, right? So if it terminates and the output starts with a 0, you output 1. In all other cases, it is 0. Okay. If terminates and output starts with a 0, you output 1. Okay. 0 if terminates output starts with a 1. Okay. Any questions about the definition of toddler? So it's a well-defined function. No matter what the program is, it is always defined. The program could be not halting, it could be going into an infinite loop, but even then, toddler of M is well-defined. It is a function. It's not some program that we define. It is a function. It is always defined. You give only zeros or ones as output. Okay. Any questions about the definition? All right. Okay. So now we are ready to state our main theorem. Toddler is uncomputable. There is no Turing machine which can compute the toddler function. All right. And I would say most of the difficulty of this theorem goes into really this sort of circularity in the definition that you run the machine on itself. Okay. Once you do that, the proof is a few lines, but again, kind of confusing because we're going to do it again. Okay. So bear with me. The proof is by contradiction. Okay. Suppose there was a machine that computed toddler. Okay, suppose there was a machine that computed the toddler function. Okay. And we want to end up at some kind of contradiction. Right? So what does this mean? Toddler we define is a function well defined on all inputs, right? And now someone claimed to you that in fact, not only is it a function, but there is actually a Turing machine which captures the behavior of toddler exactly, right? This is our magical computer / machine computing toddler. Okay, so let me call this, okay, maybe not, let me just say magical program or machine. Okay, so this is, let me call this as N. Okay, someone told you it exists. What is the machine supposed to do then? Given any input, it has to produce exactly the output of toddler, right? And if I give it some program, it has to tell me whether the program on itself does something or doesn't do something. I want to say that this gives a contradiction. Why? Any suggestions? Yeah. Right. So I mean, I actually tried it on my daughter. Where the only way to defeat a toddler is to behave like a toddler, right? So if N is behaving like a toddler, let's see what it does if you mimic the toddler's behavior, right? So what should N do when given okay? So someone told you, here's a program which is computing toddler. Now this program has its own source code, right? I'm going to run the program on its own source code and see what happens. So case one. Okay, so let's see. So what is N of this? Okay. So there are two cases now. If halts and let's say okay, let's maybe in the output is 1. Okay, if the output is 1, then what happens? Why is this bad? What is this machine supposed to do, right? It's supposed to compute toddler, so this should equal exactly what the output of toddler is on the description of this machine N. Okay, but this is not possible. Why? Because if N of N halts and the output is 1, then toddler of N by definition equals 0. Okay, if the machine on itself outputted 1, then the toddler would have said 0, but then the machine said 1. Okay, so that's a contradiction. You have a mismatch. Okay. Okay, so a contradiction and computing. Case 2. If is 0, then again it's the same issue, right? Then toddler of N equals 1 by definition. A contradiction. Okay, so not only is it possible to see that there is no machine for computing the toddler, give me any machine, I can actually find an input where they would disagree, and the input would be its own source code. Okay, any questions about this? And of course, if the machine did not halt, then obviously it's not computing toddler, because toddler always has a well-defined output, 0 or 1. It should always output 0 or 1. If it's output 0, oops, then toddler must have said 1. If it outputs 1, oops, again, you have to set 0, right? Any questions about this? Okay. So this ability that you can look at the source code and reverse it, that's what makes it so hard to compute. Okay. So in conclusion, toddler is not computable. If it were computable, then we're getting a contradiction. So it should not be computable. Okay. All right. So that's our first uncomputable function. And I mean, I think until Turing came along and came up with this notion that there could be uncomputable functions, it wasn't very clear that you could have, I mean, this is still not a very complicated function, right? You're just looking at the program and asking what it's supposed to do and doing the opposite, right? But no matter how much time I give you, there is no way to compute this function, right? So now we have like this one function that we know is uncomputable. How bad is it, right? If it's only one function, who cares? You know, there's some weird function that always does the opposite. No one cares about such functions, right? But as we will see, toddler being uncomputable, in fact, implies that many other highly practical problems are uncomputable. Okay, so we'll use toddler as kind of our starting fire to really light up our hopes of computing everything. Okay. So towards this end, another really important function that you might have seen already is something called the halting problem or the halt function. Okay, again, this is a well-defined function. You know, it always takes some string as input and gives only zeros or one. It's defined on all inputs. And what does it do? So halt views the input as two pieces. Okay. So the first piece is like the source code of a program. Okay, and the second piece is just the input of the program or Turing machine. You write it this way. And right, so it takes the source code and an input on which the machine needs to be run on. Okay, and says one if m halts when run on x. Okay, and zero else. I give you a program and an input, and I ask you a very simple question. Does this program halt on this input? Okay, and your goal is to design a program which takes the source code as input and tell me whether or not this happens. Okay, this is, you know, definitely very important. For instance, in operating systems, programming languages, and so on. If you could solve this, then you would never get a code of error, right? You wouldn't have to run the program and wait for it to crash and then see that, okay, you had a code of error. Okay, you can use it to circumvent all those issues. First, check if it's going to end up an infinite loop, and if so, then just stop. Okay, but unfortunately, as important as this problem is, there is no way to solve it. Halt is also uncomputable. Okay, there is no program which can take another program as input and tell me whether or not it will halt. Okay, yeah. it doesn't, I mean, you could try and make something like that, but even then I might change my toddler to say, okay, you run on your input with some padding, with some like in maybe zeros and ones added in the beginning, and like, can consider modified toddler function where you don't just check for whether the program is itself, but something else. Okay, so the description is not unique for the program, right? Okay, maybe the question, if I understand it correctly, was what if you restrict programs to never run on their own source code? Is that the question? Okay, yeah, so I don't think this will fix the issue, because I could add some some dummy symbols in my source code, and it will not make a difference to the actual execution, but checking this equality might become difficult. Okay. Yeah, but how do you know if whether that represents itself? Are you only checking, sort of letter to letter match with the current source code, or are you going to check for some kind of equivalence of functionality? Which one of the two? Okay, so as it turns out, checking for equivalence of functionality is itself a hard problem. It's uncomputable. So we'll talk about that in the next lecture, but that's a good fix. That's potentially a good fix. But the problem is, the way we are doing it, to just check for word to word or letter to letter similarity, then you can cheat around it. But the right thing would be to check for equivalence of functionality, but that itself is again a hard problem. Okay, as we will see. You don't know whether whatever you're getting as input is the same as itself. Okay, so I can give another string which somehow magically is the same program functionality, but it'll make it fail. Okay, so maybe okay, so to even make it clearer, as we'll see in a little bit, there are programs which will, okay, so hold on. So let me give an example first. Let me give a couple of examples, and then we'll see. Okay, so the okay. So I think the question is a good lead up to asking, is halt really a hard problem in practice? Okay, maybe it's only hard if you look at some very weird problems which kind of try to run programs on itself. But as it turns out, it's hard even without any such constraints. Okay, and we'll talk about that in a second. But first, let's make sure we understand why is halt a hard problem. Okay, so the way we'll prove this is to kind of use what we did for toddler already. So we can start from scratch. That's actually, I think, how people do it, where you can prove that halting is hard without appealing to the toddler function. But I think doing this abstraction is very helpful to pinpoint where the difficulty is coming from. And now that we know toddler is hard, we can do something like this. The way we'll prove this is if halt is was computable, then toddler as well. So this is a little bit like, the saying, if pigs can whistle, then horses can fly. I don't know where this comes from, but that's an example that's used in the book, and I've seen it other places. But basically, what we're going to say is, if halting was computable, then toddler would also be computable. But we just argued that toddler is not computable, so halting should not be computable. Okay. So, but we know toddler isn't. So this implies that halt. Okay. So intuitively, what this is saying is, imagine that someone gave you a black box, right, which solves halt. Yeah, I give you this black box, some library which does something magical and solves the halting problem. You don't know what's inside this library. You don't know what's inside this black box. All you get to do is feed some input to it and get some output to it. Okay. But they told you that this black box solves the halting problem. And what we'll say is that if you give me such a box, then I can solve the toddler function as well. Okay. So we can use this box to solve. So this is called a reduction. In some sense, we are reducing one problem to another. We're reducing solving toddler to that of solving halting problem. If someone told me how to solve the halting problem, then I can solve the toddler problem. Okay. So how do I do this? So I'm going to define a very simple routine, and I'll call it solve Todd using halt. Very unimaginative name, but that's good enough. So what is the input here? The input is the description to some machine, and we're trying to compute the toddler function. Okay, so the desired output is toddler of the description. Okay, and the magical power we have is the ability to solve the halting. All right. So any ideas on how I can do this? If I tell you can solve the halting problem, I want to say you can solve the toddler function. Yeah.
So you halt, then you run it and it's 0. All that is 0, then you just halt to 0.
I mean, this is the mystery behind toddler, right? If you think about the definition, you're asked to run a program on itself and check and do something after that. So why couldn't you just run it and did the opposite of whatever the output was? The problem was that the machine could end up in a loop. And if you end up in a loop, you never get to know what ended up happening. Okay. So to avoid that, we can do something like this. If M halts on M, then you run M on M, output the opposite of the first bit. Okay. So if the machine halts when given itself as input, you know that you ran this thing, some output was produced, maybe it started with a 0. If it starts with a 0, I'm going to say 1. If it starts with a 1, I'll say 0. Okay. Easy thing to do, right? As long as I know that the machine halts, I can simulate the behavior and get to a finite output because I know it's going to terminate, right? On the other hand, if M does not halt when given as M as input, what should we do? What should we do to compute the toddler function? Well, we just output 0, right? To recall the definition of toddler, right? If it does not terminate, you should always output 0, right? So the only difficulty in the definition of toddler really comes from the fact that I can't just run M on M and see what the answer is and decide accordingly, because it can end up in a loop and then I'm not producing any output. Okay. So the above algorithm would compute toddler if we had a program for halt. Right? If you had a program for doing halt, then you could just follow this approach and compute toddler. Okay. So this implies that halting itself is uncomputable. Okay. You can also see it like, it's not again something that you can't code up. I call this infant toddler demo because it's not really a toddler, just aspiring to be one. I also have an infant now, so. Okay. So what does infant toddler do? It's kind of trying to do what we did there, right? Without the halting subroutine. We obviously don't have a halting subroutine, but if I ask you to solve the toddler function, this is something that you would do, right? I would, maybe use my, how do I point? Okay, I can't point, but it's okay. So you can see, I do look at the function handle, get the source code as a string, and run the function on the source code. If the original output, starts with a 0, then I'm going to output 1. If the output is, something else, then I output 0. Okay. Yeah.
When we're bringing it toddlers uncomputable, and then like the output, like when it halts, output was 1, the actual one 0. How come we can't just flip the output like we do here?
Because the machine might not halt. Toddler is always well defined, right? So even if the machine did not halt, the output is defined to be 0. Okay, just like halting problem, the machine did not halt, it's just at 0, right? So if it halted, then you can just run it and find out whether it, whatever the output is. But the problem is that if I take this code and run it on some programs, this is just not going to terminate ever. Okay, and then I'm in trouble because I'm not computing the toddler function. Okay, if I only give it programs which always halt, then it would work perfectly. Okay, if I give it programs which might not halt in some cases, then I would be in trouble. Okay. All right, so which is exactly what it's doing. Like I will run the function on the source code. If the output is something, do the opposite, right? I can run infant toddler on the invert string function that we defined. Says, output of this function on its own description is 0 because, if you look at the code, I put a 0 at the very end for no reason, but just to make the output be 0. Okay. So what does invert string do? It takes the input and reverses the input. And in the source code, now the last symbol is actually a 0. So when you reverse it, you get a 0. So when I run toddler on it, you would get 1. Okay. I could ask you to run it on any other program, any other function, right? I could ask you to run it on the read text file. So what does infant, toddler, and read text file mean? You have to run read text file on its own source code, which would be a invalid file name because I don't have a file name label with this string as a name. Okay, so it would go to file not found. And the first symbol there would be I, which is not 0, so which is not 1, so the output would be 0. Okay. All right. Okay. I mean, I could do something silly like change the output to be something, and then it would change the run of infant, toddler. Okay. So this works or seemingly works, except the issue is that if the program goes into a loop, then we don't know what the output would be. Okay. And if we had a black box for halt, we can sort of shortcut that scenario. And that's exactly what this is doing. Yeah.
I understand the generic halt function is not computable,
Mhm.
but is there a way to necessarily prove that a certain chunk of code like that, for example, fits a certain grammar, necessarily halts?
Yeah, so we'll talk about that more in the next few lectures, but I think that's a nice question. And it also connects to the earlier question about what if I just restrict the program to not run on its own source code or something like that, right? Like here also, we're seeing that the difficulty comes from running M on itself. Okay. Okay, but is halt really a difficult problem? And my claim is that it indeed is a very difficult problem, even for some simple programs. Okay, just to give an idea, do you know, I mean, there's this famous problem in number theory called the Goldbach conjecture. Okay, so what does the conjecture say? It's that every even number can be written as a sum of 2 primes. Okay, so let's say any real number greater than 2 can be written as sum of 2 primes. 4 is 2 plus 2, 6 is 3 plus 3, 8 is 5 plus 3, and so on. 10 is 3 plus 7. Every even number we should be able to write it as sum of 2 primes. It's been open for like almost 400 to 500 years. Okay, and there's been a lot of work in number theory to solve it. Okay, and my claim is that whether or not the conjecture can be true can be reduced to whether or not a simple short program with almost like 10-20 lines halts. Okay, so that's the scale of difficulty of solving the halting problem. It's not just that halting is hard on some crazy programs when you give the program itself as input, but it's hard even on seemingly simple programs. Okay, so what do I mean? So let's consider the following. So I write down, okay, so just compute whether a number is prime. Let's say for a in okay, so this is just something to compute whether a number is prime. Say 1, 2, 3, 4, 5 lines. Okay, and now I can define okay, what does it do? It starts with n equals 4 and says while true, you start with Goldbach, maybe something else, temporary is false. All right, and for P in range 2, n, if is prime P and is prime n minus P. Okay, I'm just checking whether the conjecture is true. I'm checking whether I can write this number n as the difference of two things. I should say, maybe it should be, yeah, that's fine. Okay, it's true, then Goldbach n is true, and you continue. Okay, so you just break this inner loop. Right, and here you move to the next number. So all I'm doing here is writing some pseudocode to check whether the conjecture is true. I check if the number n can be written as sum of two primes. If it can, then I move to n plus 2. If I cannot, then I break. Okay, so checks whether n is sum of two primes. Okay, so altogether, this is a very simple program. It has no circularity. It's not asking to run itself on any crazy input. In fact, the input is completely irrelevant, right? The Goldbach Z here, this is completely irrelevant, right? It's not doing anything. I'm just ignoring the input completely and doing something. At the end of the day, this entire program is something like, maybe if I encode it in binary, it's going to be maybe 500 characters. Okay, maybe something more, a few hundred bits, let's say. So there's a program which is so short, it has only a few hundred bits long, just like 20 lines on it. And people have been trying for 500, 600 years to figure out if this program terminates. It has nothing to do with giving a program to itself as input and so on. We just do not know whether this program will terminate. Okay. So this is kind of to give you a sense that halt is really a hard problem. You might think, or maybe it's only complicated programs which have like thousands and thousands of lines, a lot of recursion, all those crazy things that we can't tell whether the program halts. But even simple programs like this, are really hard to tell if they halt. Okay, if you had an actual program that can decide halt, I think much of number theory would just fall to the wayside. Okay. Any questions about this? I mean, this is just a conceptual illustration of how powerful the halting problem is. Okay, it's deceptively powerful. It's only asking about termination of programs, but whether a program terminates can encode something very, very complicated about numbers, about computing itself, and so on. Okay. In fact, in the homework, we were asked to do something similar for Fermat's last theorem. There's a simple program that you can write, which, based on whether or not the program terminates, you get to know whether the conjecture is true or false. Okay. Any questions about this? Okay. So if there are no other questions, then let's take a 5-minute break. And when we come back, we will try and we'll see that basically uncomputability is also everywhere, just as computers are everywhere. Okay. So what we saw just, why does this happen now? Okay, so what we just saw is that halt hold on. All right, let me see if restarting helps. Okay. All right. Okay, cool. All right. I think the adapter failed, but thanks for lending an adapter. All right. So we just saw that halt is, kind of uncomputable, and not just on crazy programs, but even on programs that we can just write in a few 10 lines. It is a really, really hard problem. Okay. And there were a couple of questions during the break, which is, why does this code seem to get around the seeming impossibility of toddler, right? So we know that this should not be possible, like n of n equals toddler of n should not be possible, because if you output 0, then you should be outputting 1. If you're outputting 1, you should be outputting 0, right? And I would say the answer really lies in this equation here. Okay, assuming that halt is solvable, you're kind of showing that x is not equal to x equals not x. That's kind of what toddler was doing, right? So the entire argument in the reduction is that because you're ending up with this contradiction, that's why your assumption that you can check whether a program halt is not possible. Okay. So the contradiction is assuming you can do something like this. All right. Okay. So what did we just do? We did a reduction. So we showed how to solve toddler using halt. Okay. And this implied that, I mean, this kind of implies in some sense, vaguely speaking, that halting should be a harder problem than toddler, right? If you can solve the toddler halting problem, then you can solve the toddler problem. So halt is uncomputable. Okay. And we can use this more generally. And you might have seen reductions earlier in CS 180, where you kind of reduce from some problem A to a problem B. Okay, so what does this mean? Roughly speaking, it translates to something like, if I can solve problem B. Okay, if someone gave me the ability to fly, then I can also sing. Believe me, that's just as hard. Okay. So reduction from A to B means I'm solving A using a magical or some black box for B. I can use this box B however which way I want. I can call it on various kinds of inputs. I can call it multiple times. I can do something on top of it and so on. But at the end of the day, I use this box along with something else to just solve the problem A. Okay. So this has two things. So this implies that, if B is computable, then what does this say about A? I'm reducing from problem A to problem B, meaning if I can solve problem B, then I can solve problem A. So if B is computable, what should this say about A? It should say that A is also computable. Okay. So this is one implication that you can draw. This is the optimist side. The other implication is the contrapositive, right? So if A is uncomputable, then what does it say about B? B is also uncomputable. Okay, so these are what we really think of as reductions, right? I mean, they're really, I would say, bread and butter of all of computer science. No matter where you are, if you're a software engineer, you're just reducing kind of one library to something else. Or if you're if you're a programmer, you're kind of using some other libraries to do something else, right? So all of those are essentially like reductions in disguise, using one black box or one library to do something else, okay? And that has implications on what we think is kind of possible, all right? Any questions about this higher level picture? Yeah?
I don't see how the second statement directly follows from the definition. Like if I can solve B, then I can solve A.
So it would follow from the contrapositive, right? Kind of proof by contradiction. Okay. So why would this follow? That's a good question. So suppose not. If B were computable, okay, then you immediately get an algorithm for A, because that's exactly what the reduction was saying. If I could solve B, then I could solve A. Okay, so it's kind of the contrapositive, by contradiction, proof by contradiction. All right. Any other questions? Okay. All right. So there are various kinds of reductions. The way I'm defining it here, reduce from problem, if I can solve problem B, then I can solve problem A. These are technically called Turing or Cook reductions. Meaning we can use the black box for B multiple times. Okay, so I'm reducing from problem A to problem B. I have this black box for B and I'm trying to use it for problem A, and there are no constraints. You can call it how many ever times you want and do some other computation on top of it. And if you're able to solve A, then you get this reduction. Okay. Let me state one sort of dummy corollary. Okay. So I want to say that if f from 0, 1 star to 0, 1 is uncomputable, then not f is also uncomputable. Okay, it's kind of as simple a reduction as you could probably hope for. So why is this true? Well, if f was computable, if not f was computable, then you could just invert the output, right? You can run the black box for not f, you get some output, then just output the opposite of that, you get f, right? So we can reduce f to computing not f. Okay. Any questions about this? So we are reducing one problem to another problem here. It's kind of very not too informative, because we would not f seems like an immediately, it seems very close to f anyway. Okay. But you can also have more complicated reductions, right? And like in the reduction that we saw, from thought to halting, we use the halting black box kind of twice. We run m on m. If the output is 1, then we do something. I guess you could save it once, but you see the output and then do something afterward. Okay. And there are other kind of reductions called carp reductions. I would say these are kind of easier. Okay, looks like we're back. What? Okay, whoever is the host, can you make me a co-host? Hold on. Okay, I got myself covered. Don't kick me out. Okay, good. We're back. All right. So a card reduction is kind of a simpler kind of reduction where you take inputs for one problem, let's say, and you have inputs for problem B. All right. And what you do is come up with is kind of one transformation, right? Which we call R for reduction, which maps instances for A to inputs for B. Okay, it's a one-to-one map. It doesn't have to be one-to-one, but it's just R goes from inputs for A to inputs for B. And a card reduction like this, R, will have three parts to it, right? Okay, so what are the three parts? You can think of that as like specification, meaning what is it, right? So it is a map from really just binary strings to binary strings, but we view this as inputs for A and this as inputs for B. Okay. And the idea is that somehow if I ask you to solve A on some input, kind of compute A of X, you transform the input X to an input for B and then just run B on it. All right. And so the next thing is the utility, let's say, is kind of Y is the property that we want is for all X, A of X equals R of B of X. I'm sorry, the other way around. Okay, I'm transforming input for one problem to input for another. So instead of, if I want to compute the output of A on the input X, I instead run my black box B on the transformed input R. Okay, I'm not doing anything afterward. I just transform the input, run my black box on it, and then I'm done. Okay, and there should also be an implementation part, which is kind of, again, I'm just breaking it up into three phases. Okay, so we want this transformation R itself to be computable. We want a program which does this transformation, right? I have some library B which can take some input, produces some output. I have some input X that I have to compute A of X. I have a kind of a subroutine R which does this transformation and then calls the library on the transform. That's it. Okay, so that's what a reduction looks like. That's the template of a CARP reduction, which we usually think of as reductions for the most part. But it's kind of a special kind of reduction, which is a little bit simpler and reasonably useful in most contexts. Okay, any questions about the definition? Again, R operates in the space of inputs. You're transforming inputs for one problem to inputs for the other problem. Yeah.
So if you view function as an outcome, all kind of reductions, are they defined to be?
Yeah. Yeah, it's not, if it's not computable, then you're not, like, you can't use it to get the conclusions that we want. Okay, so if you think of, maybe you remember from CS 180, when you're showing this reductions between NP complete problems and so on, you're kind of doing something similar. You transform input for one problem to kind of input for the other problem. Okay, and the most important property is this guy here. We need this equality to hold for all x. Okay. All right. So instead of running A on X, which I don't know how to do, I would use my black box B on the transformed input R of X. Okay. And we want it to be computable because the conclusions that we desire need it. All right. So suppose we have a reduction function R as above. Okay. Then, the same things that we did before for general reductions would follow. If B is computable, then A is computable. If A is uncomputable, then B is uncomputable. Okay. All right. So let's see an example of it. And for the example, I'm going to define a new problem, which I'll call halt on 0. Okay. So halt on 0 is closely related to the halting problem, but it asks a seemingly simpler question, okay, which is, I take the description of a program as input, and I just want to know, does this program halt when given 0 as the input? On a fixed input, there's no m comma x here, just m. I want to know if m halts on input 0. Okay, so I just had the program. There's no other second input to run the program on, because I'm only interested in the behavior of the program on the input 0. Okay. So remember, this is just a program. Okay. Now, my claim is that halt on 0 is uncomputable, and we'll do so by reducing from halt. So we'll reduce halt to halt on 0. Okay, and the way we'll do it is, we have inputs for halt. We are going to map this to inputs for halt on 0. Right, so you have some program and the input x, right? That's what input to halt looks like. We have to map it to just a single program now. Okay, we have to map it to a single program so that m would halt on x if and only if this other program halts when given 0 as input. Okay, any suggestions on what this new program should be, what this new input for halt on 0 could be? We are only operating at the level of text files, right? Any suggestions? Okay, so again, kind of, we have m, we have x, and we want to check if m halts on x. We have to go from here to a single program right? So this is what we want R of m comma x to be, right? And it has to produce a source code of a program. Okay. Any suggestions on what the source code might be? It's actually simpler than you would think. Yeah.
So whatever the input is calculated. So whatever will have that.
Yeah, exactly. You kind of hard code x into it. Okay. So what do I mean? So I'm going to define R of m comma x, the transformation to be this new program. Okay, I'll call it def n of z, which is run eval m comma x. And in designing these reductions, we can use high-level programming languages because we can have our cake, right? So all this is doing is producing the source code of a new file. It is not running evaluation on m comma x, okay? That's just the instruction. It's only working at the level of source code, okay? It takes the source code for m, takes the source code for x, and gives a new program, which within it will say, okay, run m on x. That's it. Okay, it's not doing anything else. It's ignoring its own input completely. It's just running m on x. All right. So, and this is something kind of takes a second to understand, is that we are R is not running anything. It is just writing down the source code. It's only operating at the level of text files. It takes one text file for m, and the input x, kind of just append something on top of it, and that's all it's doing. Okay. All right. Any questions about this? And this transformation of the text files can be done by a program. Right? You just have to run this, write a new text file, so that's all fine. Okay. So we can check whether R satisfies the properties. We just We're going to use my phone's audio. Can you hear me? Okay, but I can't share the screen, so just the audio for the last 5 minutes. Okay. So if M halts on X, then N halts on all inputs, right? You know, N is something which just runs M on X, ignores its own inputs, it would halt on all inputs. In particular, it would also halt on 0. So it would also halt on 0, right? So halt on 0 of R of M comma X equals 1, okay? And same thing, if M does not halt on X, then the program would not halt on any inputs. So in particular, it would not halt on this guy as well, okay? All right. Any questions? Yeah. So X was the input to halting, right? You know, halting problem has 2 inputs, M and an arbitrary input X, okay? So whatever the input to halt is, you know, we had to compute the right answer given our black box for halting period, okay? So the way that's being exploited is you produce this new program which has M and X kind of hard coded within, right? And now if I give this as a source code and call halt on 0, it would give me the right answer. Okay, does it make sense? So we're just transforming source codes here. We're not like, you know, running a program or anything. The input to halt had a machine M and an X as input, right? You had to run M on X and check if it halted. And we reduced it to this seemingly simpler question where I just have a program. I have to check if it halts on the input being 0. Okay. Yeah.
Doesn't this not fill the description of halt on 0 because it says 0 or 1 if M halts on input 0 and 0 else, but we're also halting on 1 here. So like,
Sorry.
like it seems like we're expanding the range of.
Or no, maybe this else is a little confusing. Okay, so 0 if M does not halt on input 0. Okay, so you're right that, you know, the behavior is changing, but the answer is not changing, right? The program that you wrote down either halts on every input or does not halt on all inputs, but that's okay. We are only interested in its behavior on 0. So this equality that we want, this holds, and that's all that we care about. Okay, so if this is 1, then halt on 0 is 1. If that is 0, then halt on 0 is 0. Okay, yeah. So that's okay, right? Because we are not asking halt on 0 on M. We're asking it to run on this new program. Okay, we are never, you know, we're not running M on 0 at all. We are running this new program. We're taking this new program, and I mean, we're not running anything, but we're looking at this new program and asking, does this new program, you know, what does it do on input 0? Okay. Yeah.
So the passive are basically passive or still like as well.
Along with this kind of, you know, this, yeah, exactly.
Would you still try to like plug in 0?
No. So the input to the new program is Z, right? And I mean, we're ignoring it completely. X has been hard coded. and Z is the input to the new program, right? Halt on 0 on 0 would be like, what is N of 0? But we ignored it completely. That's okay because the behavior on 0 is completely determined by what's happening here. Yeah. We're not running eval. We're just writing down the instructions for it to run eval. Because if you run eval, then kind of, we might be stuck in a loop and it's not computable, right? So that's a good question. Like, what is the reduction doing? Okay. The reduction is just transforming the source code of M and X to the source code of this new program. Okay. It's just writing down the instructions. It's not running this command, but it's writing down the instructions of this command. Okay. And this is our new program. And all we are asking is, what does this program do if I run it on 0? Okay. So that's an important concept to keep in mind. Like somehow when we do this, the reduction is only operating on source code. It's not running anything. Okay. If you run, then you get into trouble. Okay. Any other questions? Yeah.
State here is just a placeholder. It's like a dummy.
It's just like a dummy variable. Like, you were just really going to check, what does this N of 0 do, right? Does N halt on 0 or not? That's what halt on 0 would check. And it's just a placeholder for us. Okay. So that's what reductions are. Like, you transform input for one problem to input for another, and then go from there. And in the homework, there are a few practice questions for you to practice reductions, and we'll add in more things as we go along. Okay. And I'll see you all on Monday.